Imagine that it's February 12, 2019 in California, and you're evaluating the precipitation forecast. The weather pattern over the northeastern Pacific Ocean is setting the stage for atmospheric river activity likely to impact the state over the next few days. There have already been a few atmospheric rivers, or ARs, this winter season that provided beneficial precipitation. Additional precipitation would help ensure that reservoir levels stay near normal. But too much rain could exacerbate the chance of floods and landslides. To assess potential impacts, we need more information, particularly observations over the Pacific Ocean where that atmospheric river is forming.
The Atmospheric River Program is a set of scientific and technological activities to improve our understanding of atmospheric rivers, our observations of them, and our predictions of them, and to develop tools to use that information in water management and hazard mitigation.
As part of the Atmospheric River Program, reconnaissance flights use dropsondes, airborne radio occultation, flight level observations, and radar to gather atmospheric data. Together with land-based observations and sea level pressure buoys, these make up the AR reconnaissance program.
Atmospheric river reconnaissance is critical to fill in our offshore data gaps, where satellites often can't see the low-level wind and moisture that is covered by clouds that are critical to understanding atmospheric river strength.
Development of the AR reconnaissance program has been led since 2016 by Marty Ralph, director of CW3E, along with Vijay Talapragada with the National Oceanic and Atmospheric Administration. This research and operations partnership includes the U.S. Air Force 53rd Weather Reconnaissance Squadron. The program is sponsored by the California Department of Water Resources, along with several federal agencies. CW3E partners with the National Weather Service, NWS, and other scientists from the U.S. Navy, the National Corporation for Atmospheric Research, NCAR, and the university community to direct the aircraft flights.
The atmospheric river reconnaissance observations also include surface drifting buoys that are upgraded to include surface pressure. These are often deployed from the same aircraft that deploy the dropsondes. The buoy observations provide critical information on the surface pressure distribution that we don't otherwise have over the oceans, and thus provide critical initial conditions for the numerical weather prediction models.
Numerical model forecasts on the CW3E site are crucial for anticipating potential AR impacts from this event. Integrated water vapor, IWV, and integrated vapor transport, IVT, from the CW3E site work together to help define the bounds and the magnitude of an AR. IWV shows the amount of water vapor in millimeters in the atmosphere at any location. When animated, we can see how that moisture is evolving during February 12th to 15th. IVT is more directly analogous to river flow in that it uses both atmospheric water vapor and wind to represent the transport or flow of water vapor in units of kilograms per meter per second. An IVT of 250 is used as a minimum threshold to define an AR. When viewed together, IWV values are often highest in the lower latitudes, where atmospheric moisture is generally higher. IVT, on the other hand, can peak in the mid-latitudes, as we see on February 14th, where the wind is stronger. IVT cross-sections provide a more complete view of the AR forecast for California. Here we see maximum IVT values just offshore of San Diego, in the lowest 10,000 feet of the atmosphere. The IVT magnitude plume further highlights the potential strength of the moisture transport. In this example, the GFS model is forecasting an AR with an IVT peak magnitude of 897 units and a duration of 63 hours. The AR landfall tool can give more guidance about the timing, duration, location, and probability of a landfalling AR. The left image has the forecast time period along the x-axis, marked in days from February 12th. Locations along the North American West Coast are on the y-axis and correspond with the locations shown in the map on the right. colors show the probability of a chosen IVT threshold and when it occurs. For far southern California, the forecast is for a long period from February 14th to 16th, with more than an 85% chance for IVT exceeding 250. Long-duration rainfall events are more likely to be associated with deep soil saturation and related hazards. The bars indicate the duration of AR conditions at each location with either 99%, 75%, or 50% confidence.
Landslides in unburned areas are more typically associated with long-duration rainfall events or sequences of rainfall events. This area had received above normal rainfall in January and substantial rainfall in early February from an atmospheric river storm, which may have helped to increase soil moisture, making the area more susceptible to landslides.
The February 12th forecast near San Diego predicts an AR duration of 48 to 72 hours, with a peak IVT of 750 to 1,000. That corresponds to an AR4 on the 1 to 5 ranking scale, one that is likely to have some hazardous impacts. Given the AR forecast information available at this point in time, there was enough information to prepare for a heavy precipitation event. Satellite observations show it making landfall in California. The landfall location shifts south with time, with an extended duration of AR conditions in central and southern California. In the end, areas of central and southern California experienced an AR3 storm, and around San Diego they experienced an AR4 storm. Some flooding was reported, along with other hazards related to heavy rainfall.
In Sausalito, in the San Francisco Bay Area, a landslide associated with an atmospheric river on February 14th destroyed 2 homes and damaged several others.
There were also areas that experienced lower-ranking AR conditions and benefited from the rain and snow. Observation and forecast data assisted with situational awareness in the days leading up to the AR impacts for this event. Resources from the Center for Western Weather and Water Extremes helped forecasters provide impacts-based guidance that made a difference in being prepared for this major atmospheric river event.